morning, good afternoon, good evening. Welcome to Pulsar Summit 2024. My name is Sijie, co-founder and CEO of StreamNative, one of the co-creators of Pulsar. I hope you have enjoyed the keynote session this morning. You probably already heard about the keynote today of the introduction of Ursa engine. Now I can finally publicly say more. Hence, I have kind of update my talk title to be Apache Kafka done right with Ursa engine. You're probably wondering if you are in a wrong conference. You're probably wondering why I'm not in a Pulsar Summit hearing about talk about Pulsar, why this person is standing here in front of a camera is talking about Apache Kafka. Please wait. You're not in the wrong conference. You're right in Pulsar Summit, and it's also right I'm talking about Kafka today. So Kafka was first open source in 2011 and quickly became the default infrastructure for building data streaming architectures. Some people hate it, some people love it, but nearly every technology company use it. And Kafka API itself isn't a problem. Rather, it was the implementation of Kafka that poses issues. Kafka is a well-designed piece of software that emerged during the Hadoop era, a time when most of the infrastructure software was designed for on-premise deployment and optimized for Snow network. However, it's no longer 2011. A lot has changed how we're building modern cloud infrastructure, how it changed how we're building modern cloud software. It's almost 25 years past. So if you watch keynote this morning, Matteo talked about the entire evolution of our data infrastructure in the past 25 years. We get started with this on-prem era where everything is looking deployed into private data center. There's a Snow network, and you have to optimize and design the system by moving the compute closer to storage. Fast forwarding to 2010 to 2020, the entire movement is shifting from on-premise to containerized deployment, moving to the cloud, and there's fast network and people looking into elasticity over cost. And that's where a lot of systems start embracing the architecture of separate compute from storage. And till now, we're getting into the next 10 years. We're living in a much complicated hybrid environment. It's not just cloud, it's actually hybrid. And cost is on everyone's top mind, and we have to find a way to build cost-aware and sustainable architecture that is not just scale, but is as well scale cost efficiently. So along these 25 years, computing storage network has also significantly changed how we build data streaming platforms. So in the first 10 years from 2000 to 2010, because a lot of deployment is in a slow network, you have to couple your compute and storage together. Moving to 2010 to 2020, because the network became much faster and everyone is moving into containerized environment, you have to decouple that for scalability. While a lot of us change in terms of how we store data in the cloud and how data has been kind of collected in object storage and stored in a standard lakehouse format. So the way how we use storage has been significant change, while it's still decoupled from compute, but the way how stored data is also changed in the past 5 years. But yet, the entire Apache Kafka implementation has remained more or less the same. So many organizations have tried to kind of move Kafka to their cloud environment, but few are really true satisfied about the result. Yet you still hear tons of the Kafka pain points, and all these pain points are coming from different places, Someone would say Kafka is too expensive to run in cloud. Kafka is too hard to scale. And some people might even say Kafka is written in Java, so let's rewrite it in using C++. Oh well. But Kafka has a lot of pain points. But really, what is the pain point in that is reflecting in today's environment is actually boiled down into one major pain point is cost. And what does that cost mean? We have to kind of do a little bit kind of analysis on the cost of running a Kafka infrastructure or Kafka software. That really boils down into three aspects. One is infrastructure cost. Secondly is the operational cost. Lastly would be the integration cost. So infrastructure cost is Kafka is designed with a coupled architecture, meaning I have to over provisioning the resources because the storage and compute are coupled. And it was designed as an AP system, rely on replication across different availability zone for reliability. So there's massive cross-AG network coming from data replication. And usually people will miss one hidden networking cost coming from data rebalancing. When you do data rebalancing, there's tons of data moving across different availability zones. And it's also really expensive to store long-term data. With all this taken into consideration, Kafka requires data rebalancing, meaning you have to spend tons of your SRE hours to do operation such capacity planning, scaling up your cluster, scaling down your cluster, taking out the failure nodes, and managing and support many different components within the Kafka ecosystem. And while you have the Kafka infrastructure standing up ready, you have the SRE team to operate that system, but your data engineer would need to process the data. And reprocessing historical data in Kafka is really expensive due to massive network cost. And you also have to hire a bunch of the data engineers, build bespoke integrations that to ingest your streaming data into Lakehouse. That bespoke integration would take tons of the wasteful resources. And also because the data is sitting in different systems, there's a duplication, there's errors in mapping schemas between data streams in your data lake tables. So putting all this together, we know Kafka is expensive based on the existing implementation, but Kafka API itself is not a problem. So our answer to this essentially is taking Kafka API and provide a more cloud native implementation that is suitable for the current environment where everyone is care about cost. And that's URSA. That's what we introduced in the keynote. So let me walk you through our entire journey in terms of how we are making sure Kafka implementation is done right. So first of all, we have to understand how Kafka stored the data, how the original architecture is coming from. Kafka was designed in 2011, so where the compute and storage are coupled together because of slow network. And you have the broker that is deployed across different availability zones and rely on data replication to making sure the data is reliable, replicate across different regions, availability zone. And so the majority of the cost is actually first coming out from this architecture require data rebalance. So let's see, can we remove the data rebalance? Removing the data rebalance would actually taking out the majority of the costs, such as over provisioning. You need to hire a team of a couple SREs to operate the Kafka cluster to scaling up, scaling down. So we took the first step is introducing a separation between compute and storage, and that's the fundamental architectural difference that we did in the first version of Pulsar. We moved the storage nodes into a separate layer. We call it a storage layer, and leaving broker became a stateless broker, so it doesn't store any data. This separation result in instant scalability without over provisioning. If you need more data, you just need increasing the number of the storage nodes. If you need more computing power, you're just scaling up your broker, which is able to make us scale like thousands faster than Kafka, which also with this decouple, there's no data rebalance anymore. It actually improved the latency, throughput, and as well as make the system become more reliable. And because you don't need to over provision the data, you don't need to do data rebalance, you save tons of the resources in network, which will result in about 60% of the cost reduction. Now we successfully remove the data rebalance. Let's review the cost of Kafka. On the infrastructure cost side, there's no over provisioning anymore. You can just scale the resources you need. There's no data rebalance, so there's no networking cost involved in data rebalance. And you don't, because of the decoupling, there's no data rebalance required, so you don't need to hire tons of resources to do capacity planning. You don't need to spending your operational hours to scaling up the cluster, scaling down the cluster. The cost is already reduced time. So that's looking into next one. Now you have the Kafka system up running. You want to store data more, but you quickly realize if I put all the data in local storage or using EBS volume and require replicate data across multiple availability zones, it's very expensive to store data for much longer term. So we took next step to kind of really think about how we can achieve much lower cost to store data for longer duration. So we do an exercise to kind of really turn Pulsar inside out to understand how we store data. So if you're looking into this layer, the storage layer is actually powered by a system called Apache Bookkeeper, which is a storage for write-ahead log and bunch of the data segments. You can think about write-ahead log is designed for fast writes, and those data segments are materialized data that is able to serve fast reads and as well as like read by certain offset. So after taking that abstraction, we have thinking about, because the data is organizing in data segments, so if I move some of the older data segments into much cheaper storage, then we can reduce the entire cost of storage, which we can make the system is able to store cost effective for the long-term data. So we introduced tier storage back in 2018, moved the code data segment to the object store. So we are able to store the data segments in much longer duration in a much lower cost. So once we did that, let's review the cost of running a Kafka. Essentially, now we take out the cost of storing long-term data and move the storage to a more cost-efficient object storage that almost every cloud provider provided. Now, the cost is reduced further. We have to really kind of think about now the data is stored there, but if I don't use it, why I'm storing data in the object store? So in order to make usage of those data, we want to make the data stream immediately available in the lakehouse. So in that way, we can also reduce the cost of bespoke integrations that I need to ingest data into your lakehouse for analysis. So to take that kind of one more step to kind of really think about what data is organized in the object store, essentially is individual data segments, which is stored in Pulsar's own format, and it's not useful for a lot of the other open lakehouse analytic ecosystem. So we have kind of really think, do we really need to store the data in Pulsar's own format? Can we just format the data in lakehouse open formats like Hoodie, Delta Lake, and Iceberg? So we take one more step to evolve our tier storage to lakehouse storage. We convert all the data stored in tier storage to table format streams, and that's what we call lakehouse storage. So with lakehouse storage, it actually connecting data stream with a broader data lakehouse ecosystem. All the data stream into the Ursa engine would become immediately available as ready to use lakehouse tables. So then you can use any query engines that work with these lakehouse tables, such as Redshift, Snowflake, BigQueries, Asina, Spark, Flink. So you unlock tons of opportunity there. And you, more importantly, it removes the entire bespoke integration between data streaming and data lake. And you don't need to hire additional data engineering team to build integrations there. You don't need to have additional resources to run those integrations. And that's come back to really review the cost again. You will see further reduction coming out for these efforts. The entire integration cost is gone because the data getting into data streaming platform is immediately available as ready to use lakehouse tables. So you don't need additional cost to do the integration, ingestion, and as well as development of those pipeline. And one thing I want to really call out, making data really available in a lakehouse ready format, which also remove the needs of reprocessing the entire historical data in a streaming system, because if you're reading from a streaming system, replaying all this historical data, you will result in tons of the network costs, and that is already gone. You can build a more cost-effective ETL pipeline, transform those tables entirely in your lake without kind of going back to your data streams to process those data. Now, the final pieces is still remaining is actually we still have tons of the cross-AZ network coming out from data replication, because the system was originally designed as an AP system, which care more about the availability and low latency and performance. But can we really kind of rethink about the way how we use the data and how we replicate data? Can we use some of the other replication mechanism to making sure the data is still highly available, but we are able to achieve much efficient kind of replication mechanism? So that's all coming into the concept of removing keepers. We'll probably not cover about removing zookeeper in this talk because it's more focused on the metadata, but we will talk more about removing bookkeeper because that is where the entire cost is coming from for replicate data across different availability zones. So the way how we evolve our system is not about kind of rewriting the entire system. Bookkeeper was introduced for a certain reason. It was designed as a low latency log storage. It optimized latency over the cost. So it's actually a secret sauce of Pulsar be able to scale 1,000 times faster than Kafka. So the problem of the bookkeeper essentially is a trade off the latency over the networking cost. So the thinking here is, can we introduce some sort of more cost optimized write-ahead log implementation, which could leverage maybe object store for replication? Then we should be able to remove the entire class AZ traffic, and it will make the entire system much easier to run. Hence, the entire removing bookkeeper becoming introducing a cost optimized write-ahead log, which would allow us to do more cost-effective, high-volume data streaming with high availability while still maintain really low cost. Maybe you will see a little bit kind of increase on the latency side, going from single-digit latency to 100 millisecond or 200 millisecond, but not worse than that. So the entire system becoming pluggable, that you have both cost optimized write-ahead log, which is powered by object store, you write directly to S3, and at the same time, you are able to opt in a latency optimized write-ahead log, which is powered by Bookkeeper. Said if you still have financial applications that care a lot about latency, you can continue using the latency optimized write-ahead log. If you have use cases like metrics logs that doesn't care a lot about latency, but you want to achieve cost-effective, high volume data streaming, you can use this cost optimized write-ahead log that is purely based on object store. And putting all this together, combining like Ursa engine is a multi-tenant engine. The way we think about this is not you would have two different clusters. One is designed for cost optimized, the other is designed for latency optimized. We actually have the ability to really put all this into one system, and that you choose different optimizations there on a per tenant basis. So you can have a tenant that is cost optimized, and you have another tenant that is latency optimized, and that optimization, the choice of optimization is not just in the tenant level. You can all the way to cascade down from tenants, namespace, and topic. You have the flexibility to choose what is the right optimization that we want to use, and you still manage it in one cluster without having to maintaining like hundreds of clusters to meet different requirements. So now we are at a point, we are really comfortable and happy about all the efforts we took into removing the cost that is coming out from the Kafka design. Now there's no cross AG network traffic anymore. The cost is reduced to an extreme. So all this is the evolvement, how we are turning system implementation that was coming out 20 years ago into an implementation that is fitting into current cloud native cost conscious environment. And lastly, I want to kind of highlight one thing Matteo is calling out in the keynote is our ambition of for data streaming platform is always to be unified, meaning I have the ability to take in different streaming protocols, messaging protocols, and make the developer doesn't need to switch from one protocol to the other protocol. So Ursa engine is where we really achieve that ambition is we're putting Kafka API and Pulsar API together. You are able to do both data streaming and messaging queue together in a very cost-effective way, and that meets current environment. And finally, when we're putting all this together, you will see the entire Ursa engine became a multi-protocol engine. We support both Kafka API natively. We also support Pulsar API natively. It's actually a multi-tenant solution, which you can have different tenants sitting in one cluster and optimize the resource to extreme. And you don't need to manage hundreds of clusters, you just manage one. And let different tenants have different quota, have different resource control, and be able to choose the right optimization for their use cases. And lastly, the entire storage engine within Ursa has evolved into a multi-model storage engine, which store both data streams, and those data streams can be formatted as lakehouse tables. This would unblock a lot of integrations. You don't need to do any bespoke integration, moving data stream to data lake tables. It's all in one storage. And this is the entire new evolution in terms of how we are making Kafka implementation to be done right in a cloud native, cost conscious environment. And all this is not purely new. It actually coming out from a collection of efforts that we have done in the past 2 years, which including making Ursa engine Kafka API compatible, making the data store as table formats, remove Zookeeper by introducing a much scalable Oksha, removing Bookkeeper by introducing cost-optimized write log implementation on object storage, and lastly, we are able to writing the data streams as lakehouse tables. While our ambition doesn't really start here, eventually we want to making sure the lakehouse tables that store in object store can also be read as data streams. So in that way, we are really connecting all the application domain and the analytic domain together, and with one modern data streaming stack. With all this Ursa engine, we really making Kafka much easier to run and deploy in a modern cloud. It's much faster than any Kafka implementations, and it's much cheaper to deploy and run and maintain and operate. And that's the entire presentation about how we make Apache Kafka done right with Ursa engine in the cost-conscious data streaming era. And all this functionality is now available on StreamNative. You're welcome to sign up and check it out. If you have any question, please do reach out to us. We would like to work with you in shaping the future of data streaming. And thank you for coming to my talk, and hope you enjoy the rest of the talks in Pulsar Summit. Thank you, everyone.